Hi, today we're going to talk about atomic mass, atomic weight, the difference between those two, and how to calculate atomic weight. So if you look at an average element and how it's represented on the periodic table, you may see a number of different things on the periodic table depending on which version you're using, but most of these things have three common elements. The first is a symbol for the element that it represents. The second is the atomic number, Z, which is basically the number of protons. And then we have this thing which is often referred to as the atomic weight. Now, depending on what order you're getting instruction in, you may have already learned about molar mass, and you might say, hey, isn't that molar mass? Yes, that is also molar mass, and that's why there are no units on the periodic table. But when we're talking about atomic weight, there are three different units that you may see associated with it. The first is an oldie that is pretty much out of date at this point. It's atomic mass units, AMU. I'm trying not to use that anymore, but it is definitely what they were using when I first learned chemistry back in the dark ages, so sometimes I slip up. Most modern chemists and physicists use U, the unified atomic mass unit. If you're a biologist or a biochemist, you're going to use Daltons. Now, all of these things refer to the same unit, which is defined as 1/12 the mass of a carbon-12 atom. That is an atom with 6 protons and 6 neutrons. So why do we talk about atomic mass and atomic weight? Why don't those two things mean the same thing? So when you talk about atomic mass, you're talking about a particular atom and what its mass is. With atomic weight, you're talking about an average. What is the average mass, a statistically weighted average mass, of a generic atom of a particular element? An analogy using things that are a little easier for us to look at. If I asked you for the mass of this apple, you could take it and you could stick it on your balance and you could tell me the mass in grams. That's pretty easy. But what if I said, hey, I need you to get me 2 kilograms of apples because I want to make an apple pie. Now, you could take the mass of the one apple that you had just weighed and divide 2 kilograms by that mass and assume that's the number of apples you need to get. But not all apples are the same size. Some of them are bigger than others. So what we need in order to be able to give a number of apples for that is to actually go through, find a large number of apples, weigh all of them, divide by the number of apples, and see what the average mass is. When we talk about a statistically weighted average mass, that's basically where we're talking about sorting them. So let's say we sort them into size groups, which actually does happen in the supermarket, which is why you can get the really small apples for cheap and then the larger apples are more expensive. But you could say, okay, 10% of apples weigh under 100 grams. 25% of apples weigh between 100 and 150 grams, and so on and so forth. And from this distribution of masses, you can figure out what your average mass is going to be. So when we calculate atomic weight for a particular element, what we're going to do is we're going to look at the mass of one of the isotopes. We're going to multiply that by the abundance of that isotope, and we're going to use a decimal rather than a percent when we do that. And then we'll keep doing that for each isotope that we have, add up the total contributions, and that will give us our atomic weight. Now, this makes a lot more sense, as usual, if you actually have a real example in front of you. So let's go back to carbon. Carbon has 2 primary isotopes. People often ask me about carbon-14, but the truth is that carbon-14 makes up, if I remember correctly, 0.001% of all carbon. So it basically does not really contribute much to the average atomic mass at all. So let's just look at carbon-12 and carbon-13. So remember, step 1 is multiply the atomic mass of each isotope by the abundance of that isotope. So what we have here, we have the mass of carbon-12, which is exactly 12.000, because that's how we define the U or the Dalton, times the abundance expressed as a decimal. So we convert 98.93% into 0.9893, and that gives us 11.8716. Now we're going to do the exact same calculation with carbon-13. So the mass of carbon-13 times the abundance as a decimal instead of a percent. That gives us 0.1391. When you add these both up, which is step 2, what you get is 12.0107. And that is the atomic weight of carbon. Now, if you remember back to the periodic table entry that I showed you for carbon, it's a 12.011, so that's rounded a bit, but this is the average atomic mass of carbon. So I start with carbon because it only has 2 isotopes, and that makes it easy to calculate, but you can do this with any number of isotopes. So here's neon. Neon has 3 primary isotopes, neon 20, neon 21, and neon 22. So we first start by multiplying the atomic mass of each isotope by the abundance of that isotope, and you can see for neon 20, that's going to be 19.992 times 0.9048. That gives us a little over 18. Neon 21 times 0.0027, and you can see that's a very small number. Neon 22 times 0.0925 gives us a little over 2. When we add those together, we get basically 20.18. Now, if you go back and you look at the individual parts of each of these calculations we did, you can see that most of that 20.18 comes from neon 20, and that makes sense because neon 20 comprises most of the neon atoms we encounter. So one thing you can do beforehand is you can predict by looking at the isotopes and their abundance what your atomic weight will be. In this particular case, I look and I see neon 20 has a much higher abundance than neon 21 or 22, so I am pretty sure that the atomic weight will be about 20. But I also see that neon 22 is going to contribute a fair amount, so it will actually be a little above 20. So you can see that is actually where it ended up. Basically, when you look at that mass on the periodic table, it represents 2 things. The molar mass, which gets talked about in a different video, which is the mass of a mole of that element, and also the atomic weight, which represents the average mass of an average atom of that element. The reason we can use these averages is because when we're talking about moles of stuff, we're talking about so many atoms that statistically you're likely to get the average value. I hope this was helpful, and I look forward to seeing you again soon.